4.4 Modeling with volumes of revolution. Now, volumes of revolution can be used to model real-life situations, and we'll take a look at an example to illustrate this. Example number 4. The diagram shows a model of a goldfish bowl. The cross-section of the model is described by the curve with parametric equations x equals 2 sine t, y equals 2 cos t plus 2, and t is in between pi over 6 and 11 pi over 6. And the units of x and y are in centimeters. The goldfish bowl is formed by rotating this curve about the y-axis to form a solid of revolution. And for part A, we have to find the volume of water required to fill the model to a height of 3 centimeters. So for this question, what you need to recognize, we're rotating about the y-axis. Now, if you remember, of course, here, first of all, you'd see the equations are defined parametrically. So if we take a look at what we mentioned here, when we're rotating about the y-axis, the formula for the volume of revolution is shown here. So we know already x is equal to 2 times by the sine of t, and therefore x squared, that will equal 4 sine squared t. Now, we know already y is equal to 2 cos t plus 2. So therefore, if we differentiate to find out what dy over dt is, hopefully here you can see this is minus 2 sine t. So we've got what x squared is, we've got what dy over dt is. We need to now change our limits in terms of y to limits in terms of t. So you can see here, when y is equal to 0, so we're starting over here, we have over here 2 cos t plus 2 equals 0. Cos t is equal to minus 1. T is equal to pi. And when y is equal to 3, because it says here to a height of 3 centimeters, we have 2 cos t plus 2 equals 3. So if we rearrange, we can see that cos t, that's going to equal 1/2. And therefore, t is either equal to pi over 3, or it's equal to 5 pi over 3. And the reason we want to find out the 5 pi over 3, we want to make sure our limits are shown over here. So if we now substitute everything in as necessary, what we have over here then is the volume, which is equal to pi, lots of the integral from pi to 5 pi over 3 of x squared, which is 4 sine squared t, lots of dy over dt. So we have over here minus 2 sine t, and we're integrating with respect to t. So now we need to tidy all of this up. 4 times by minus 2, that's minus 8, so let's take out the minus 8. So we've got minus 8 pi, lots of the integral from pi to 5 pi over 3 of sine squared t, lots of sine t. Now, we can technically write this as sine cubed t and then use some of the stuff which we met earlier in Dumoir's theorem to help us integrate this, but that will be too much effort because first of all we'll have to think about the complex numbers, etc. But instead what we can do is rewrite sine squared t as 1 minus cos squared t, and you'll see why I'm doing that in a second. So we've got minus 8 pi, lots of the integral from pi to 5 pi over 3 of sine t, lots of 1 minus cos squared t dt. So now if we expand this into the bracket, we've got minus 8 pi, lots of the integral from pi to 5 pi over 3 of sine t minus sine t times by cos squared t, which I'm going to write as cos t all squared dt. So now to do this, you can see the differential of cos, that's outside the bracket, that's minus sine. So here we can use the reverse chain rule to integrate this bit here. So if we integrate sine t, we get minus cos t. So we've got minus 8 pi times by minus cos t. Now if we use the reverse chain rule, add 1 to the power. So here we get sine t lots of cos t to the power of 3, divide by the new power, divide by the differential of the bracket. And then we're going to evaluate this between pi and 5 pi over 3. So if we tidy this up even more, we've got minus 8 pi, lots of minus cos t plus 1/3 of cos cubed t. And we're going to evaluate this between pi and 5 pi over 3. So now we need to substitute for our upper and lower limits. So if we substitute for our upper limit, we have minus 8 pi, lots of minus cosine of 5 pi over 3 plus 1/3 times by the cosine of 5 pi over 3 cubed. And then we have minus 8 pi, so that will be plus 8 pi, lots of minus cos of pi plus 1/3 times by the cos of pi cubed. So this is what we get when we substitute in for our lower limit. So here, what we end up with is, if we work all of this out, we'll end up with minus 8 pi, lots of minus 9 over 8, which is equal to 9 pi units cubed. So this is our final answer. And now for part B of the question, the real goldfish bowl has a maximum diameter of 48 centimeters, and we have to find the volume of water required to fill the real goldfish bowl to the corresponding height. So what you can see over here is the model has a maximum diameter of 4 centimeters, but the real goldfish bowl has a maximum diameter of 48 centimeters. So hopefully what you can see the linear scale factor, that will equal 48 divided by 4, which is equal to 12. So therefore the volume scale factor, that's equal to 12 cubed. So therefore the volume in actual tank, that will equal 12 cubed, which is our volume scale factor, times by the volume which we got for the model, which was 9 pi. If we work all of this out to 3 significant figures, we get 48900 centimeters cubed. So this is how we approach modeling questions.